Hello everyone, my name is Tong Liu, come from Shanghai University. It is my great honor to be here to present my paper, Joint Location Value Privacy Protection for Spatiotemporal Data Collection via Mobile Crowdsensing. This is the outline of my presentation. Firstly, I will introduce the background of our work. With the popularization of intelligent devices, mobile crowdsensing is proposed, which utilize the smart devices equipped with sensors to collect data. However, as participants need to upload personal information to the central platform, which may disclose their privacy, registered users will be reluctant to take part in tasks which lead to the crowdsensing system will fail to get accurate data. Hence, in our work, we focus on the privacy protection in mobile crowdsensing-based spatiotemporal data collection. Then, I will introduce the motivation of our work by giving an example to show how privacy is leaked and obtain some insights for our approach design. Suppose there is a platform requiring users to collect ambient noise from various interested locations. A location privacy preserving mechanism is provided to perturb their original locations to other possible locations with a certain probability. For example, there is a user in the system whose real trajectory is ABBC. The user collects 20 dB, 35 dB, 30 dB, and 50 dB of noise in location A, B, and C over 4 time slots. At the second time slot, the user perturbs his location B to F, as shown in the figure. In addition, we assume the platform can obtain relatively accurate estimations of the noise in each location from a group of users. Then, according to the locations of the user in the first and third time slots, the platform can infer that the possible location of the user in the second time slot can be D, B, or E. By comparing the estimated values of these three locations with the sensed values collected by the user in the second time slot, the platform can successfully infer that the real location of the user in the second time slot is B. From this example, we can find that only perturbing the locations contained in sensing data collected by a user is not enough. We must protect location value privacy jointly. Next, I will present the system model of our work. In our work, we consider a typical crowd-sensing system consists of a central platform located in cloud and a set of registered users equipped with smart devices. The platform is responsible for publishing tasks to registered users and estimates true values after users upload location-based and time-sensitive sensing data around several interested locations continuously. The locations of interested points in the urban area are represented as L. For convenience, we divide time into equal interval time slots, denoted by T. Submitting original sensed values and locations of users will expose their private information like trajectories to the platform and adversaries, since an untrusted platform may leak privacy of users for commercial interests and financial benefits, or be attacked by adversaries. In this work, we consider users preserve their privacy information by submitting sanitized values of sensing data and perturbed locations to the platform. With receiving all sensing data collected in a time slot, the platform aggregates all sanitized values around an interested location according to their perturbed locations, as shown in the figure. Then the platform can obtain the estimated value of the location in the time slot by employing truth estimation. In the next, I will introduce some preliminaries about truth discovery and local differential privacy. Local differential privacy is a promising technology used to provide privacy protection with a quantified guarantee, which is applied to the systems without a trusted third party. Due to the property of local differential privacy, we can design privacy protection mechanism which satisfies local differential privacy. Then the level of privacy protection can be measured by privacy budget epsilon and the relaxation variable delta. A lower value of privacy budget and the relaxation variable indicates a stronger privacy protection value can be achieved. Given initial weights of users, truth discovery can compute the estimated value of each interested point and update weights of users iteratively until the estimated value converge. So we can utilize truth discovery to get truth value and assess the accuracy of our proposed approach. In what follows, I will introduce our proposed privacy protection approach, which includes two mechanisms for preserving location privacy and the sensed value privacy of users, respectively. Firstly, I will show the overview of our approach. As shown in the figure, in each time slot, each user firstly collects the sensed value of the monitored object in his current location. Then each user performs the LPPM and the VPPM mechanisms locally and independently to perturb the location and sanitize the sensed value respectively. Finally, the perturbed location and sanitized sensed value, as well as the identity of the user and the timestamp, are submitted to the platform. The platform first aggregates sanitized values according to the perturbed locations of users after receiving all sanitized sensing data. Then, based on the sanitized values in each location, the platform conducts the truth discovery method to estimate the truth value of the monitored object in each location at the current time slot. So our proposed privacy protection approach includes two mechanisms, which are location privacy preserving mechanism and value privacy preserving mechanism. In order to protect the location privacy of users, we brought location privacy preserving mechanism based on random response. By setting a predefined perturbing probability P, the original location of a user can be perturbed to another interested location with probability P divided by m-1 and remain unchanged with probability 1 minus P. The location privacy preserving mechanism satisfies local differential privacy. In addition, we can find When perturbation probability P becomes larger or the size of location set becomes smaller, the privacy budget becomes smaller, which indicates a higher value of privacy protection, vice versa. Besides perturbing locations of users, their sensed values should be sanitized as well. The platform first published a predefined parameter lambda to all users. Then each user generates a private Gaussian distribution where variance is sampled from the exponential distribution with parameter lambda, and then samples noise from this private Gaussian distribution. The value privacy preserving mechanism we propose also satisfies local differential privacy. We can discover that the variance of the Gaussian distribution becomes larger. The lower bound of the privacy budget becomes smaller. While the value of parameter lambda is smaller, the lower bound of the reaction variable will be smaller. Then, we introduced experiments to evaluate the performance achieved by our proposed approach. The baselines used for comparison is listed as follows. In NPP approach, each user submits the original sensing data, then the estimated values obtained by truth discovery. In OLS weight approach, each user submits the original locations and sanitized values, then the estimated values obtained by truth discovery. In PLOV approach, each user submits the perturbed locations by LPPM mechanism and the original values, then the estimated values obtained by truth discovery. In the PPM approach, each user submits the perturbed locations and the sanitized values obtained by our mechanism, then the estimated values obtained by taking the average of the sanitized values. Besides, we use MAE and accuracy as the evaluation metrics, which are calculated as the two equations. We take different numbers of interested locations into consideration to compare the MAE and accuracy achieved by our privacy-preserving approach and other baselines. Firstly, we plot the MAE and the accuracy achieved by the 5 approaches when the number of locations varies from 5 to 25 in the 2 figures. It can be found that the MAE and the accuracy of our approach remain stable, which indicates that our approach is scalable to the amount of interested points, especially when our approach can achieve about 94% accuracy of estimate values, which is only 8.13% lower than NPP, 7.26% lower than OLSV, and 1.94% lower than PLV approach, but 4.67% higher than the PMM approach. Secondly, we evaluate the performance of the 5 approaches by varying the total number of users from 200 to 1,000. It can be observed that the MAE and the accuracy achieved by our approach keeps stable regardless of the number of users, which indicates that our approach applies to a large-scale mobile crowd sensing system with plenty of users. especially when there are 200 users. Our approach achieves 91.68% accuracy, which is only 7.51% slower than NPP, 6.36% slower than OLSV, 3.41% slower than PLOV, respectively. Finally, I will summarize our work. In this work, we consider the joint location value privacy protection problem in a mobile crowd-sensing system with an untrusted platform. Since not only location tags, but also sensed values of users contained in their spatial-temporal sensing data will expose the privacy. Therefore, we propose a privacy protection approach comprising of two privacy-preserving mechanisms to perturb the locations and sense the values of users respectively. Especially the location privacy-preserving mechanism is designed based on random response, and the value privacy-preserving mechanism is designed based on Gaussian mechanism. Both of the two mechanisms are proved to satisfy local differential privacy. Moreover, we conducted extensive simulations to show that the true values in interest locations can be accurately estimated based on perturbed locations and sanitized sensed values by adopting the truth discovery method. So that's all. Thank you for your listening.